Hey kiddos, and welcome to our last section of Chapter 2, which is all about kinetic, potential, and mechanical energy. Today's talk is about mechanical energy. Put your thinking caps on because we're going to have some fun. Alrighty, so very quickly, what is mechanical energy? The term mechanical energy means the sum. And when you're talking about sum, you're adding two things, right? Two or more things of an object's potential and kinetic energy. So when we have our potential and we have some kinetic, because you can't have one without the other, right? You can't have potential energy without having the thought of kinetic energy. So if you add those two together, you have something called mechanical energy. It's your EK plus your EP. When work is done on an object, the object gains energy as well. This is another important thing. We're dealing with work too. So work, this is all transfer of energy, kiddos. Work can be transferred, work energy can be transferred directly into potential energy and directly into kinetic energy depending on the circumstance. Okay, that's very, very important. And we're assuming, of course, that it's a closed system, so there's no loss of energy due to friction, etc., which you know is not real life. An object is gaining kinetic energy if it increases its speed, which we know from kinetic energy, right? From the formula 1/2 mv squared. An object is gaining gravitational potential energy if it is getting higher above the reference point, which we know that because of the formula EP equals mgh. Okay, that's it. That's all. That's it for theory. Let's go right into examples. So a seagull flying horizontally at 8 meters per second. So let's unpack the question. It's moving at 8 meters per second. We know that's our speed. Carries the clam with a mass of 300 grams. That's our mass of the clam. In its beak, calculate the total mechanical energy of the clam when the seagull is 3 meters above the ground. Okay, so we've unpacked our question. Now what we're going to do is we're going to write everything we know. We know that our speed is equal to 8.00 meters per second. No big deal. We know that our mass of the clam is 300 grams. We know also that grams isn't going to cut it. We have to convert to kilograms, which is 0.300 kilograms. So far, so good, kiddos. And we were also given the height, which is 30 meters. Okay, awesome. So now what we have to do is we have to figure out our mechanical energy. So I'm going to go ahead and write the formula. EM is equal to EK plus EP. We know this. So now what we have to do is we have to kind of include the formulas of EK and EP. So EM is equal to 1/2 mv squared, right, for kinetic energy, plus mgh. Right, kiddos? So let's go ahead and do some work. So for our kinetic energy part, EM is equal to 1/2, right? And I'm going to, in there, I'm going to write 0.3 kilograms. Multiply that by 8.00 meters per second, and that has to be squared, right? So I'm just going to work on this half first, but you can definitely work on it linearly, but for right now, I'm just going to work on this. My EM is equal to, so far, 9.6 joules. So once I do all my math, I get my answer to be 9.6 joules. So I have to square the 8 meters per second, multiply that by 0.3, divide that by 2, and I get 9.6. But now I'm going to worry about my EM, or my, my potential energy, which is mgh. Apologies. So I have my mass at 0.3 kilograms, and I have my g, which is 9.81 meters per second squared, and multiply that by my height, which is 30 meters. If I do all the math, I get 88.29 joules. Now I'm adding these two, right? So now I'm going to add these two. So my EM is going to equal to, and I'll write it prettier, 88.29 joules plus 9.6 joules, so it doesn't matter which goes first, is equal to 97.9 joules. And that's our answer, kiddos. Okay, let's move on to the next one. 55 kilogram high jump athlete leaps into the air in an attempt to clear the bar. So we have a mass, right? It's already in kilograms, so we're good to go. So attempts to clear the bar. At the top of the leap, the athlete has a total, now they're given the total mechanical energy. So your total mechanical energy is 3.00 times 10 to the power 3 joules and is moving, here's our speed, at 8.33 meters per second. What we need to do is we need to calculate the gravitational potential energy of the athlete. So I'm going to give you different ways of how to do this. I'm going to give it to you where I'm manipulating the formula, and I'll also go through some examples where I don't manipulate the formula. I just go ahead and use algebra, because algebra is our friend. Either way, we're going to write down what we know. Our mass is 55 kilograms, no big deal. Our EM, which is given to us, is 3.00 times 10 to the power of 3 joules. And we also know our speed, which is 8.33 meters per second, and also going to identify the fact that we're looking for our potential energy, right? So here's our formula. EM is equal to EK plus EP. Now what I'm going to do is I'm going to rearrange the formula, right? And I'm going to make sure I'm isolating the EP. EP is equal to EM minus EK. Okay, that's our new formula. So now let's start breaking this down, because we know our EM, right? EP is equal to 3.00 times 10 to the power 3, subtract 1/2 mv squared. Right, kiddos? So EP is equal to 3.00 times 10 to the power of 3, subtract 1/2, and I'm going to write down my 55 kilograms for my math, and 8.33 meters per second squared. Okay, moving on. EP is equal to 3.00. Isn't this fun? Just rewriting things over again. Subtract 1908.19 number joules. EP is equal to let's subtract the 2, which is going to give you an answer of 109 times 10 to the power of 3 joules. All right, kiddos? So in this case here, what I did is I manipulated the formula to find my potential energy. Okay, moving on. A construction worker drops a 2-kilogram hammer from the roof. Okay, there's a mass. We've been given some kind of mass. When the hammer is 50 meters, that's our height, above the ground, it has a total mechanical energy, oh great, another one of these, of 1.88 times 10 to the power 3 joules. Calculate the kinetic energy of the hammer. So the question before this, we were asking for the potential energy. Now we're looking for the kinetic energy. This time, I'm going to manipulate the formula again. So first write out everything that we know. Mass is equal to 2.00 kilograms. Height is equal to 50 meters. And we have our EM, which is equal to 1.88 times 10 to the power of 3 joules. Okay, we also know that EM is equal to EK plus EP, right? But now we're going to look for EK. EK is equal to EM minus EP. Okay, cool. So now EK is equal to our EM subtract mgh, which is our formula for EP, right? EP is equal to mgh. So we're going to use that. Our EK is equal to 1.88 times 10 to the power of 3 joules. Subtract that by my mgh. I'm going to extrapolate on that. 2.00 kilograms, that's the mass, multiplied by my 9.81 meters per second squared, and multiply that by my height, which is 50 meters, right? EK is equal to 1.880 joules. I'm just going back and forth from scientific notation to not scientific notation, but you can leave it in scientific notation, that's fine. 981 joules. My EK then is equal to 899 joules. Okay, cool. So now that we know what mechanical energy is, it's the addition of my kinetic energy plus my total potential energy. So now we're going to take it a little step further and understand what is going on in terms of the transfer of energy. Okay, the law of conservation of mechanical energy states that within a closed system, closed or isolated system, right? So that means we're not taking into account friction, that kind of thing. Energy can change form, so it goes between potential and kinetic, but the total amount of mechanical energy remains constant. Okay, so the number, the mechanical energy doesn't change. Your EK is always going to, your EK plus your EP is always going to equal your EM. But we can, what that means, what this concept means is that you can change stuff around. I'll show you that in just a second. A closed isolated system, recall, means that it is isolated from external forces, so no work can be done on it. Energy can't be added or taken away. It is sometimes referred as a frictional system, which you know is not real life. But in real life, friction dissipates energy as useless heat. All this really means is that potential energy is being converted to kinetic energy or vice versa. So we can say that our EK is equal to our EP, or the change in EK is equal to the change in EP. We can extrapolate that and say 1/2 mv squared is equal to mgh. Now, you can divide both sides by the mass. So if there's a transfer of energy and we have the concept that there's no loss, we can remove mass because mass is going to be the same on both sides. And you know that 50 and 50 on the one side and 50 on the other side, if you get rid of one or the other, you're dividing, so it gets rid of it anyways. So we get this cool little thing where 1/2 E squared is equal to GH. So back to what I was talking about, that the fact that EM is equal to EK plus EP, right? This never changes. So if this is 100, I can have 50 plus 50. So 50 joules of kinetic energy plus 50 joules of potential energy is going to give me 100 joules of mechanical energy. This doesn't change, right? So I can have 100 joules, but I can change in here. I can have 60 joules of potential kinetic energy. If I have 60 joules of kinetic energy, kiddos, I have no choice. I have to have 40 here. 40 joules of potential energy because it's still going to equal to 100 when I add it up. That's all this concept is saying. But the total amount of mechanical energy remains the same, but there can have a change in form of kinetic and potential energy, as long as they add up always to the mechanical energy. Okay, that was fun. So let's take a look at some questions. A 10 kilogram water balloon, so here's some information, is dropped from a height of 12 meters. Okay, calculate the speed of the balloon before it hits the ground. So before we start anything, let's write everything down. We have our mass is equal to 10.0 kilograms. We have our height, which is equal to 12.0 meters. And we're also identifying the fact that we are looking for the speed. Okay? In this case, I think we're pretty cool in understanding what is going on. It tells you that EP is equal to, let's first of all find our EP, right? Because we can't find the speed without the kinetic energy. And we're not given the kinetic energy. So we can find the potential energy because we have our mass and our height, right? mgh. So EP is equal to your mass, which is 10.0 kilograms, times 9.81 meters per second squared. And we're going to multiply that by our height, which is 12 meters. So our EP then is equal to 1,177.2 joules, let's just say. So we also know the concept that EP is equal to EK. So if there's a potential and energy of 1,177.2 joules, we can say that that could be transferred exactly to kinetic energy, right? So now we have EK is equal to 1177.2 joules. Now that we have this, now that we have this, we can find our speed. Make sense, kiddos? So let's go ahead and manipulate the formula. V squared is equal to 2ek over r mass. V squared is equal to 2 times 1177.2 joules over 10. V squared is equal to 235.44, oops, right? And now what we're going to do, meters per second, is we're going to take the square root, because we're not asked to find the v squared, we're asking to find our simple speed, which is equal to 15.3 meters per second. So this takes on to the fact that the concept of the direct transfer of energy. We were able to find the potential energy of 1,177.2 joules. Because that's potential energy, we know that we can transfer that to kinetic energy, and we're going to make the assumption that there's no loss. So now that we have our kinetic energy, we can definitely find our speed. Okay, not too bad. Next question. A 30-kilogram child on a trampoline, okay, let me just write this down or unpack the question, jumps on a trampoline vertically into the air at an initial speed of 1.60 meters per second, and we're looking for the height. So let's go ahead and write everything down, shall we? We have our mass, which is equal to 30 kilograms. We have our speed, which is equal to 1.60 meters per second. And that's pretty much it. And we're also asked to find our height. So we know that height is found in our EP formula. And we can't really use that because we're also having to accommodate the fact that we need to use our speed. So first thing we're going to do is we're going to find our EK, because we can. mv squared, right? So our EK is equal to our mass, which is 30.0 kilograms. And I'm going to multiply that by my 1.60 meters per second squared. Our EK is then equal to 38.4 joules of energy, right? We also know that EK is equal to EP. So if our EK is 38.4 joules, we know that our EP is going to be 38.4 joules also. So now that I have that, I can add that to our list of what we know, 38.4 joules. Now that we have this, we can find the height, because the height shows up in our EM formula, right? So our EP, or our potential energy formula, I should say, mgh, EP is equal to our mass, which is 30 kilograms, times our 9.81 meters per second squared, plus height, and that's what we're looking for, right, kiddos? So in this case here, I'm not going to manipulate my formula. I'm just going to go ahead and use algebra. So our EP is 38.4 joules is equal to 30 kilograms multiplied by 9.81, which is going to give you 294. And we multiply that by our height, right? We're going to look for height, so we have to divide this by 294 to cancel it out. Divide that by 294. And we get our height is equal to 0.1306 meters. Our height then is equal to 0.131 meters. Okay, awesome. Next question. A 20-gram dart is fired from a dart gun with a horizontal speed of 4.10. So we have a mass here. which is equal to 20.0 grams. If we had to change it to kilograms, which we do, 0.020 kilograms, okay? And it's traveling at a horizontal speed of 4.10 meters per second. Our speed is equal to 4.10 meters per second. The total mechanical energy, love those, is 0.481 joules. So our EM is equal to 0.481 joules. And we want to calculate the gravitational potential energy. So our EP is equal to, that's what we're looking for, right? So we know, now this one here, I'm actually not going to manipulate the formula, so you can see that there's different ways to do it. EM is equal to EP plus EK, right? Our EM is a given 0.481 joules is equal to our EP, which is what we're looking for, plus 1/2 mv squared. So 0.481 joules is equal to EP plus, now I'm going to go ahead and write everything down. Our mass, oops. Okay, let's do that again. 1/2 times our mass, 0.020, and multiply that by 4.10 meters per second, second squared. So 0.481 joules equals to EP plus 0.1681 joules. All right, so I'm going to get rid of this. I have to subtract 0.1681 joules. That cancels out, so then I have to subtract 0.1681, which is going to give me EP is equal to 0.3129 joules, which is going to be equal to 0.313 joules. Okay, kiddos, so this is how you do it without having to manipulate the formula first and using our friend called algebra. Okay, final question. A pendulum consists of a 500-gram metal ball. So our mass is equal to 500 grams or 0.5 kilograms, right? Suspended on a 50-centimeter string. Cool. The ball is pulled horizontally and up a total vertical distance of 10.0 centimeters. So that's your height, not the 50. The 50 can be only if it reaches 0 at the very bottom, but I'll explain that in a bit. So we know that our height is equal to 10.0 centimeters, right? Or 0.10 meters. Okay, so it is then released. At the bottom of the arc, the mechanical energy of the ball was determined to be, so our EM is 0.491 joules. What was the speed of the ball? So we're looking for speed. If you want, you can even put G is equal to 9.81 meters per second squared. Just looks cool. So we know that our EM, because, okay, it says here, is pulled and up a total vertical distance. So that's the total vertical distance. We know that EM is equal to EK in this case. So EK is also equal to 0.491 joules. Okay, so our EK is equal to 1/2 mv squared, and we know that our EK is equal to 0.491 joules is equal to 1/2 0.50 kilograms times our v squared. 0.491 joules is equal to 0.25 kilograms times our v squared. Again, I'm not manipulating my formula. So what I need to do here is I need to get rid of the 0.25. So divide that, 0.25 kilograms, which is going to give me 1.964 is equal to my v squared. I have to take the square root. My speed is equal to 1.40 meters per second. Okay? If you wanted to do it the other way, I can just go v squared is equal to 2ek. Oops. I'm just showing you how it would look like if I manipulated the formula. V squared is equal to 2ek over m. V squared is equal to 2 times 0.491 joules over 0.5 kilograms. And I'm still going to get my v squared is equal to 1.964, whereas my speed is equal to 1.4 meters per second. So either way, you have both. Now the reason why EM is equal to EK is because, and it was the speed at the very bottom of this arc. So when the speed is at the very bottom of the arc, it's actually 100% kinetic energy. That's why in this case, EM is equal to EK. And I'll show you that in the next little while so that you have a better understanding of what the heck is going on. Okay? So here we have the conversion of mechanical energy in a pendulum. So anytime you have a pendulum question, you have to understand what's going on with each of these positions. Okay? In this position here, let's just say it's as high as it can go. Okay? In this position here, you have 100% potential energy, right? Look over here in position number 3. And I'll show you this really, I'll articulate this. In position number 3, there's no height. And in position 1, it's the highest height compared to when you're comparing to all of these. So here, EK, right, is 100%. So in this case here, with EP being 100%, EP is equal to EM, in this case here in position 1. In position 3, because it's 100% kinetic energy, EK is equal to EM, right? These positions, anywhere in between there, that's where you have to say, okay, EM is equal to EK plus EP. But I'll articulate that much better. So the sum of kinetic energy and potential energy is called mechanical energy, but we're looking at mechanical energy in terms of a pendulum. So in position 1, in this position, the bob is about to be released. Therefore, we have no EK, right? Because it's not moving. We're holding this, and it's about to be released. It also means that we are at a maximum height, so the mechanical energy is equal to EP only. And that's where you get for bob 1, EK plus EP, and we have our 1/2 mv squared plus mgh. Because our speed is 0, okay, this will be 0, we have EM is equal to mgh. That's just for position 1. That's just the math that shows that I'm not lying in terms of the pendulum. Position 2, in this position we see that the bob of the pendulum is swinging downwards, therefore we have movement, which means we have an increasing EK. So as we release the bob, the potential energy is going to go down and the kinetic energy is going up. Also, the height of the bob is getting smaller, so that means that we have a decrease in EP. So EM is equal to the sum of EK plus EP. Okay, so anywhere in here, in between this spot here, we have EM is equal to EK plus EP. Okay, keep in mind that EM is equal, the EM here is also equal to the EM here, mechanical energy here, which is equal to the mechanical energy here, which is equal to the mechanical energy here, which is equal to the mechanical energy here. We can't change mechanical energy, but there is a transfer between kinetic and potential. So in position 3, we notice that there's no height. Okay, so in position 3, it's 100% kinetic energy. In this position, we see that the bob is at its lowest point, therefore we have no EP. It also means that the bob is at its fastest speed, since EM is equal to EK only. Okay, so basically why? Because there's no height. If there's no height, EP is equal to 0. So that's why your EM is equal to your 1/2 mv squared only at position 3. Okay. Keep in mind that the EM does not change because of the law of conservation of energy. So even though this is 100% EK, in this case here EM is equal to EK, but EM doesn't change here. Mechanical energy for all these positions stays the same. So no matter where we are in the swing of the pendulum, the mechanical energy value is a constant one and is always calculated by adding the EK and the EP at that position or point in time. Okay, that's it, kiddos. That was a long one. I'm so sorry. I don't think you need to make the notes. Just give a little reading of energy conversions. I'm not going to test you on it, just so you know. Have a great day.